Hello viewers, in this video we will see the problems on thermodynamics topic. This is part 2. So here we will be discussing problems related to the topics second law of thermodynamics, entropy, heat engine, Carnot engine. So related to these topics we will see some of the problems which is related to NEET exam. Okay, we will also see some previous year asked questions in NEET and some problems related to NEET exam. So as usual I have given a Google form which consists of 15 questions. In which the link has been displayed in the, it has been given in the Google, description box. So kindly make use of it for your practice. Okay. So now we'll go to the problems. So see the first problem. Here they given, here is a refrigerator problem. See the coefficient of performance of a refrigerator is given as 5. So the value of COP is given as 5 in this problem. So if the temperature inside the freezer is, okay, so normally in case of a refrigerator, we will have a low temperature reservoir, work input, and we have a high temperature reservoir. This we are considered as T2, this is as T1. Here they given the low temperature reservoir temperature as minus 20 degrees Celsius. So T2 is given as minus 20 degrees Celsius. Here we have to convert the temperature into Kelvin. Okay, so minus 20 to convert into Kelvin, we have to add 273, which is equal to 253 Kelvin. The T2 is given as 253 Kelvin. What is the question asked? The temperature of the surroundings to which rejects heat. So they've asking the temperature of the high temperature reservoir, that is T1. Okay, we have to find the value of T1. So what is the formula for COP in terms of temperature in case of a refrigerator? It is T2 by T1 minus T2. So here they given the value of COP. So you know the value of T2, 253. So T1 minus T2. Okay, so take this value to the left hand side. So we'll be having so 5T1 my T2 value is 253. You know that. So 5 into 253. So 253 into 5, 5 and 1. So sorry. So 1265. So 1265 which is equal to 253. So 5T1 will be equal to 253 plus 1265. So 253 means it is 8. So it is, so T1 is equal to 1518 by 5. Okay, so when you do this calculation, you'll be getting approximately 303.9, which is equal to 304 Kelvin. So the value of the temperature we have got is 304 Kelvin, but the answers are given in degrees Celsius. We have to convert this value into degrees Celsius. So what you have to do, you have to minus by 273, we'll be getting 31 degrees Celsius. Okay, 31 degrees Celsius. So option B is the right answer. Okay. So it has been asked in NEET 2015. Okay, fine. Second problem. See, in this problem, given a refrigerator works between the temperature limits are 4 degrees Celsius and 30 degrees Celsius. So the low temperature is 4 and the high temperature is 30 degrees Celsius. So it is required to remove, because the work of refrigerator is to observe the heat. For that, work input will be given and some heat will be liberated to outside. Okay, so here we are removing 600 calories of heat every second. Okay, so the heat removed here is, the Q2 is 600 calories per second. In order to keep the temperature of the refrigerator space constant. So to maintain the temperature constant, we have to remove this amount of heat. So what is the power required? Okay, so what is the power required of the refrigerator? So first thing, from COP of the refrigerator, you have heat observed. For that, what is the work done? Okay, this is the formula. First, we have to find the value of COP. So here the temperature, low temperature is again 4 degrees Celsius. Convert this into Kelvin. So it is 4 plus 273, which is equal to 277. Here it is 30 plus 273, which is equal to 303 Kelvin. Okay, so COP is nothing but T2 by T1 minus T2, which is equal to 277 divided by 303 minus 277, which is equal to 277 divided by, you will be getting 26, 277 by 26. So this value will be approximately 10.65. So the COP value is 10.65. Now you know the value of COP is 10.65. So here 10.65 is equal to, we have to remove 600 calories. So here the value should not be in calories, it should be converted into joules. Okay, so how to convert into joules? Sorry, in question itself they are given. So 1 calorie is equal to 4.2 joules. Okay, so 1 calorie is equal to 4.2 joules. So convert this 600 to 4.2, you will be getting approximately the value as 2520 joules per second. Okay, as it is calories per second, it's joules per second. Okay, so 600 into, so this Q2 value will become 2520. So I have converted into joules by the work done. So work done will be equal to 2520 by 10.65 will be approximately it is 236.5 joules per second. Because for the amount of work done, what is the power required? So the power required and work done will be same. So this work done is can be also converted as power. So joules per second is nothing but watt. So the answer is 236.5 watts. Okay. Okay, the third problem. See, in this problem, a gas is compressed isothermally to half its initial value. So this is the initial value. It is compressed to half through isothermal process. Next, the same gas, the same amount of gas is compressed separately through an adiabatic process. So the same compression is done by an adiabatic process. So now what is the question? To half its volume. Okay. Then see that what is the condition given? Compressing the gas isothermally will require more work to be done. Then compressing the gas through adiabatically will require more work to be done. Then compressing the gas either isothermally or adiabatically will require the same amount of work. Which of the case requires more work will depend upon the atomicity of the gas. Okay, so you have to choose what is the right option. So work done. So work done can be calculated from the PV diagram. So here we have a PV diagram. See that. So here the gas is compressed. So the volume gets reduced. So we have V1. This is as V2. I will do it here. I don't know whether it will be visible or not. I will do it here. Let's see whether it is visible or not. Okay, fine. So we have V1 and this is V2. So volume gets compressed. So in case of an isothermal process, you see that you will be getting a curve, a slope, slightly a steep curve. You will be nodding it. So in case of isothermal process, you will be getting a steep curve. So this is an isothermal process. Okay. So you know the value of slope. The slope of isothermal process is, this value is minus P by V. Okay, in case of isothermal process. In case of an adiabatic process, you see that the slope of adiabatic is always greater than the slope of isothermal process, which is equal to minus gamma into P by V. It is gamma times greater than the isothermal process. So the slope of adiabatic process is always greater than isothermal. So the curve will be more steep. The curve will be more steep when compared to isothermal. Okay, this is an adiabatic. Okay, so it is moved from 1 to 2. So from the graph we can see that the area exposed, the area covered by the curves is more in case of adiabatic process. Okay, so for this isothermal, this is the curve. Adiabatic, this is the curve. So the area covered by the adiabatic process is more when compared to isothermal. So the work done will be more in case of your adiabatic process. So option B will be your right answer. Okay. Okay, the fourth problem. See, in this problem, the temperature inside a refrigerator is given as T2, small T2 degrees Celsius, and the room temperature is given as T1 degree Celsius. The amount of heat delivered to the room, see, they are asking the amount of heat delivered to the room, that is the temperature, the heat given outside that is a hot reservoir. Okay, the heat is asked for each joule of electrical energy consumed. For the consumption of the electrical energy, that is the work done. Okay, because by consuming electrical energy only, the work will be done. So what is the amount of heat delivered with respect to the work done or with respect to the consumption of heat electrical energy? So they are asking this value, that is amount of heat delivered with respect to the work done. So this expression, this value is being asked in this question. Okay. So let us start with respect to the COP. So the COP, we know that it is heat absorbed by work done. Okay, but they are asking Q1 by W. Okay, let us see. Wait. So you know the formula for COP with respect to temperature is T2 by T1 minus T2. But here they are given in terms of small t. So T2 divided by T1 minus T2. Okay, this is the COP. But you know the COP is also equal to Q2 by W. Okay, so here you know this W is equal to Q1 minus Q2. So here instead of Q2 I am going to replace it by Q1. So Q1 could be written as, so here Q1, sorry, in case of Q2 we have to replace Q2 in terms of Q1 minus W. So Q2 will be equal to Q1 minus W. So Q2 is equal to Q1 minus W. Just replace this bar. So COP will be equal to Q1 minus W by W, which is equal to Q1 by W minus 1. Okay, so now equate this both equations. Okay, so now T2 by T1 minus T2 will be equal to Q1 by W minus 1. Now take this 1 to this side. So you will be having T2 by T1 minus T2 plus 1 will be equal to Q1 by W. Take the LCM. So here I am writing here. So T2 plus, when you take the LCM, divide by T1 minus T2, which is equal to Q1 by W. So from this T2 will get cancelled. So what is remaining here? The remaining is T1 by T1 minus T2, which is equal to Q1 by W. Now I'm going to represent the temperatures in Kelvin. Okay, so if it is Kelvin means here this value could be written as T1 plus 273. So bottom it is T1 plus 273 minus T2 minus 273. So it will also become, when you multiply by minus, it will become minus. So this 273 will cancel. So the final final answer will be, I am writing here, T1 plus 273 by T1 minus T2, which is equal to Q1 by W. Okay, so from this we can see option D will be your right answer. So Q1 by W value is T1 plus 273 by T1 minus T2. Okay, thank you. Okay, the fifth problem. See, in this problem, here they given the Carnot engine having an efficiency of 1 by 10 as heat engine is used as a refrigerator. Okay, so if the work done on the system is 10 joules, so see here a Carnot engine having efficiency of 1 by 10 as heat engine is used as a refrigerator. So if the work done on a system is 10 joules, okay, so the efficiency is given as 1 by 10 and the work done is given as 10 joules. Okay, so normally you know the efficiency formula is nothing but work done by heat supplied. Okay, so here we can write it is given as 10 joules and the efficiency is given as 1 by 10 by heat supplied. So from this the Q1 value is, it is 100 joules. So in case of a heat engine, it is the heat or energy observed, but when it is used as a refrigerator, we see that it is the heat released to the atmosphere, okay, or hot reservoir temperature. But what is the question asked? The amount of heat energy observed from the reservoir at low temperature, because in case of refrigerator, the role of refrigerator is to observe the heat energy at low temperature reservoir. So we have to find that one. So they are asking Q2. Okay, so now you know Q1, you know W, you can easily find the value of Q2 because you know W is equal to Q1 minus Q2. So from this Q2 is nothing but Q1 minus W. So which is equal to Q1 is 100 minus 10, which is equal to 90 joules. So the amount of energy observed from the reservoir at low temperature is 90 joules. Option A is the right answer. Okay. Okay, the sixth problem. See, in case of sixth problem, the efficiency of an ideal heat engine working between the freezing point and boiling point of water. So the two temperatures limits are, one is freezing point and boiling point. Freezing point, you know, it is 0 degrees Celsius, and then boiling point 100 degrees Celsius. So between those two temperatures, the heat engine has been working. So they are asking what will be the efficiency of this heat engine. Okay, so The efficiency, you know that in terms of temperature, it is T1 minus T2 divided by T1. Okay. So when you convert this into Kelvin, it will becomes, this will be equal to 273 Kelvin and this will be equal to 373 Kelvin. So when you have 273 by 100, it will be 373 Kelvin. So here 373 minus 273 by 373 into 100. So when you do this calculations, okay, you will be getting the value of percentage as 26.8%. Okay, you do this calculation, you will be getting the value as 26.8 percentage. Okay, so next one, see the increase in temperature of a gas filled in a container would lead to, okay, so what happens when the temperature of a gas filled in a container increases? Four options: we decrease in intermolecular, increase in its mass, increase in its kinetic energy, decrease in its pressure. See, normally when temperatures increase, what happens? The molecules will get energy and it moves with the kinetic energy. It moves because there is an increase in kinetic energy. Okay, so normally the kinetic energy of the molecules only will increase when the temperature increases. Okay, your eighth problem. See, in this problem they are given two cylinders having mass as m1 gram and m2 gram of a gas at pressures P1 and P2. So, given the pressures as P1 and P2 respectively, they are put in communication with each other. When they are put in communication, that is, when they are combined together by keeping the temperature constant, what will be the common pressure reached will be when they are combined together? What is the pressure, common pressure reached? The expression for the pressure they've asked, so they are given four options. Okay, so see, they are given two gases. So according to this ideal gas equation, we have PV is equal to mu RT, in which mu is nothing but number of moles. In which mu is nothing but number of moles. So this mu could be replaced by small m by capital M, because mu is nothing but amount of substance, that is nothing but mass by molar mass. This capital M is molar mass. So mass by molar mass will give you the value of amount of substance. Okay, so this PV could be written as M by capital M into RT. So now we substitute this with respect to 1 and 2. So for the first case we have, for the first mass, so P1 V1 will be equal to M1 by capital M into RT. For the second one, we have P2 V2 is equal to M2 by capital M into RT, because the same gas is being used, so the molar mass remains the same. Okay, so now when it is combined, see, when the gases are combined, see what will be the expression, this expression P into V1 plus V2. As it is combined, we will be having V1 plus V2, which is equal to M1 plus M2 divided by capital M into RT. Okay, so now from this equation I am going to write separately for V1. V1 could be written as M1 by M into P1 into RT. So here similarly V2 is equal to M2 by capital M P2 into RT. Now substitute the values of V1 and V2 in this equation. Okay, so substitute the values of V1 and V2 in this equation. So here it will be written as, see, I am writing here. So P into, instead of this V1, M1 by RT, so plus so here it will be M1 plus M2 by capital M into RT. Okay, so from this we can take RT by M as common. It remains as common for both sides of the equations. Okay, so here M1 by M1 by P1 plus M2 by P2. So I am taking RT by M as common. So here also so RT by M remains common on both sides, so it could be cancelled. So I have to find the expression for this P. So take LCM in this side. Okay, in this side, the left hand side equations. I'm going to take LCM in this equation. So it will be written as P into, so in denominator we will be having P1 P2, numerator will be having P2 M1 plus P1 M2. Okay, So which is equal to m1 plus m2. Right? So take this denominator p1, p2 to the right hand side. So the expression changes as p is equal to, see, p1, p2, m1 plus m2 divided by, so by taking this value to the denominator, it will be written as p2 m1 plus p1 m2. So this is the final expression for the value of p. Okay, so from this we can see option D is the right answer. Okay. Okay, the ninth problem. See, here they given a Carnot engine operates with the source at 127 degrees Celsius and sink at 27 degrees Celsius. Okay. Sorry, if the source supplies 40 kilojoules of heat energy, the work done by the engine is. So heat is supplied, value is given. They're asking the what is the work done by the engine. So see, source means the heat supplied area. Okay, so source is heat supplied area. Sink means heat rejected area. Okay, so here it is hot reservoir. This is your cold reservoir. Okay, so source. It means that the temperature is given as 127 degrees Celsius. So 127 plus 273 is equal to 400 Kelvin. So we have T2 is equal to 27 degrees Celsius, which is equal to 27 plus 273, which is equal to 300 Kelvin. So the efficiency in terms of temperature is of a Carnot engine is 1 minus T2 by T1, which is equal to 1 minus 300 by 400, which is equal to 1 minus 3 by 4, which is equal to 1 by 4. So the efficiency is 1 by 4. So what is another formula for efficiency? You know that efficiency is equal to work done by heat supplied. So 1 by 4 work done, you have to find it by 40 kilojoules. So from this we can see that W is equal to 40 by 4, which is equal to 10 kilojoules. So option C is the right answer. Problem. See, in this problem they are given two cylinders A and B fitted with piston. Okay, so if you are here having two cylinders fitted with piston. Okay, they are fitted with piston. So this is A and this is B. Okay, they contains equal amount of ideal diatomic gas. So they are having gas. Okay, the same amount of gas, it is maintained at the temperature 300 Kelvin. Okay, so the piston of A, see, the piston of A is free to move, while that of B is held fixed. It is not free to move, it is held fixed. Okay, so same amount of heat is given to gas in each cylinder. So same amount of heat is given to both the cylinders. What is the question asked? If the rise in temperature of the gas A is 30 Kelvin. So normally both the gas, the temperature is 300 Kelvin. If the rise in temperature of A is 30 Kelvin, what will be the rise in temperature of the gas in B? Okay, that is the question they have given. Okay, so it is A. In A, see that the piston is free to move. So here you can consider the heat supplied could be written as mu Cp delta T. This mu Cp delta T, because the piston is free to move. So let us take it as the work is done under constant pressure. So it is mu Cp delta T. Mu is nothing but number of moles, Cp delta T in case of A. So in case of B, here we can see that the piston is held fixed. Oh, so the heat supplied will be equal to takes place at constant volume. Okay, so because when heat is supplied at constant volume, see that there is only change in internal energy. There is no work done at all. So QB is equal to mu Cv delta T. So heat supplied at constant volume, mu Cp delta T. So here they given that same amount of heat is given to gas in each cylinder. It means that QA is equal to QB. So here it is mu Cp delta. See, here it is A and this is B. Delta TA, which is equal to mu Cv delta Tb. Okay, so number of moles gets cancelled because the same gas is used. So here Cp by Cv, I am taking Cv here, into delta Ta will be equal to delta Tb value. Here it is given as, so sorry, we have to find the value of delta Tb. So delta Ta value is given as 30 Kelvin. Okay, so Cp by Cv value, you know that Cp by Cv, you know Cp by Cv is nothing but gamma. Okay, so in case of a diatomic gas, the value of gamma is nothing but it is 1.4. Okay, now substitute, now replace the Cp by Cv in terms of 1.4. Now you know the delta T value is given as 30 Kelvin. So into 30 will be equal to, when you multiply this value, you'll be getting it as 42 Kelvin. So delta T value is 42 Kelvin. Okay. 11th and 12th question. See in this 11th question, see that a house refrigerator with this door open is switched on. So see that the door of the refrigerator is opened and it is switched on in a closed room. So the air in the room is, what happens to the air in the room? Whether it will be cooled or it will be heated. That will be the two conditions. So see that when the door is opened of a refrigerator, see that now the low temperature will be, that is the temperature of the refrigerator will be equal to the atmospheric temperatures. Okay, so the inlet temperature will be equal to the atmospheric temperature. So what happens to the outlet temperature, or what happens to the outlet heat? The heat will be increased, because in case of refrigerator, you know that heat is being absorbed at low temperature, and that is at Q1, and it is that is Q2, and it is released as Q1. This is the low temperature reservoir, this is a high temperature reservoir. Okay, that high temperature reservoir is released to the room. Okay, so now what happens to the room temperature? Automatically it will get increased, because as the door is opened, we see that the refrigerator will be exposed to the room temperature. Okay, so that temperature itself is more. So what happens to this temperature? This will be more. The room will get heated. Okay, the heat is increased, the heat released to the room will get increased. So automatically here we see that the room gets heated. We cannot use refrigerator as air conditioner. Okay. Okay, that is the answer for the 11th one. Now we see for 12th one. See, a heat engine receives heat at the rate of 2500 kilojoules per minute. So the heat received at the rate of 2500 kilojoules per minute and gives an output of 12.4 kilowatt. So the output is 12.4 kilowatt. What is the efficiency? So you know the efficiency is work done by heat supplied. Okay, so we have to find the efficiency. So work done, it is given as 12.4 kilowatt by, so here the value is given as 2500 kilojoules per minute. We have to convert it into 2500 kilojoules per second. So divide it by 60. Okay, so here it will become 2500. When you take 60 to the numerator, so 12.4 60 2500. Here this will be, you will be getting the value as 0.29. Okay, you will be getting as 0. Approximately it is 0.3. So they have asked the value in percentage. So you have to multiply by 100. So we will be getting it as 30%. So 30% is the right answer. Okay. See, a refrigerator removes 50 kilowatt from a heat sink. Okay, refrigerator means the low temperature reservoir is given as 50 kilowatt amount of heat removed. The temperature of the heat sink is the high temperature reservoir. Temperature is 250 Kelvin, and the temperature of the heat reservoir is, the heat sink temperature is 250 Kelvin. And the heat reservoir, that is the hot reservoir, that is given as 300 Kelvin. So temperature values are given, and the heat absorbed value is also given 50 kilowatt. Power required of the refrigerator is. Okay, so here you know that COP, you know that here the values are given in terms of Kelvin. So it is 250 divided by 300 minus 250 will be 250 by 5. 50 will be equal to 5. So COP value is 5 here. So you know that COP is equal to heat absorbed divided by work done. So heat absorbed is 50 kilowatt divided by work done. Okay, so COP is given as 5. So the work done will be equal to 50 by 5, which is equal to 10 kilowatt. So 10 kilowatt is the right answer. Okay. So now the next problem. Here we can see that so one heat engine operates between 1000 Kelvin and T2 Kelvin. Okay. Another heat engine operates between T2 Kelvin and 400 Kelvin. Both the engines have the same heat input and output. It means that both the engines have same heat input and output. It means that both the engines have same efficiency. Then the temperature T2 value is equal to. Okay. So if they have the same efficiency, what will be the value of temperature T2 is? So here first condition, the T1 is given as 1000 Kelvin. 1000 Kelvin, and a T2 is given as T2 itself, T2 Kelvin. In second case, T1 is given as T2 and a T2 is given as 400 Kelvin. Okay, so you know that the efficiency is equal for both the engines. So efficiency is equal to, for the first case, for the first case, it is written as 1000 minus T2 divided by 1000. Because generally we have formula T1 minus T2 by T1. This is the efficiency formula. So I have written for the first case. For second case, efficiency is equal to T2 minus 400 by T2. This is the formula for the second case. So you know that both the efficiency are equal. Okay, so now we have to equate this. Both the efficiency are equal. Equate this equation. So 1000 minus T2 by 1000 is equal to T2 minus 400 by T2. So when you cross multiply, it is 1000 T2 minus T2 square is equal to minus 4, 1, 2, 3, 4, 5. Okay. So from here we can see that this 1000 T2 and 1000 T2 gets cancelled. Okay. So here I am writing. So T2 square will be equal to 1, 2, 3, 4, 5. So from this T2 will be equal to square root of 1, 2, 3, 4, 5. So when you do the square root of this value, you will be getting the answer as 632.5 Kelvin. So T2 value is 632.5 Kelvin. In the question, which of the following statements considering entropy are correct? Okay, so here we have three statements. Entropy is conserved in all reversible process. Yes, because the change in entropy is constant, so we can say the entropy is constant because there is no change of entropy in case of a reversible process. Okay, so the entropy is always concerned in case of your reversible process. Entropy of substance is least in solid solution. Yes, in case of solid solution, now see that the molecules will not move. Okay, so there will be no randomness of molecules. So there will be, see that the entropy substance will be least in case of solid solution when compared to liquids and gases. Okay, the randomness of molecules is very less when compared to liquids and gases. So it is least in case of a solid solution. Okay. Next we have entropy of a solid solution is not zero at absolute zero temperature. Yes, only for perfect crystalline solid is zero as according to the third law of thermodynamics. I would consider other solid solutions, it is not zero at the absolute zero temperature. Okay, so all the three options are right. Oh, I forgot to write the options. Okay, so the options here are the options 1 and 2 only, and B 2 only, and C 1, 2 and 3, and option D 2 and 3 only. So from this we can see that option C is the right answer. All the three are correct. Okay, okay, fine. Now the 16th question. See, here we have 1 kg of ice at 0 degrees Celsius melts to water at 0 degrees Celsius. Okay, so the resulting change in its entropy, taking latent heat of ice as 80 calories per gram degree Celsius. So you have four options. So you know that change in entropy is equal to delta Q by T for constant temperatures. For absolute value of temperature, this is the formula. Okay, so what is the heat supplied here? So the latent heat of heat is given and mass is given. So the heat will be equal to mass into latent heat. So mass is given in kg. We have to convert it into grams because latent heat is given in terms of grams. Okay, so 1000 into 80 grams. Okay, so 1000 into 80 grams. The temperature is 0 degrees Celsius. We have to convert it into Kelvin because all the options are given in Kelvin. So it is equal to 80 into 1000 divided by 273. When you do this calculation, you will be getting as 293, approximately 293 calories per Kelvin. Okay, so then option C is the right answer. Okay. 17th problem. See, here the given a Carnot engine use low temperature reservoirs are 7 degrees Celsius. Okay, so we have T2 as 7 degrees Celsius. Okay, has an efficiency of 50%. So we has an efficiency of 50%. So it is desired to increase the efficiency by 70%. So second case you see that the T2 remains as 7 degrees Celsius, the efficiency as 70%. So by how many degrees should the temperature of the high temperature reservoir be increased? For this increase of 70%, what is the level of high temperature increased? So we have to find the value of high temperature with respect to this efficiency and this efficiency. Okay, we'll find it. You know that efficiency is equal to T1 minus T2 by T1. So this is 0.5. is equal to T1 minus, it is 7 degree means it is 280. Okay, so 280 Kelvin by T1. So when you do the calculation, it is 0.5 T1 which is equal to T1 minus 280. So when you do the calculation, it is 280 by 0.5 which will be equal to 560 Kelvin. So 560 Kelvin in case of this equations. For this one here, efficiency is equal to T1 minus T2. It is taken as T1 dash. T1 dash. So here it is 0.7 is equal to T1 dash minus, it is also 280 by T1 dash. So 0.7 T1 dash is equal to T1 dash minus 280. So T1 dash minus it will be equal to T1 dash is equal to 280 by point is equal to, you'll be getting it as 933 Kelvin. Okay, so when you do this calculation, you'll be getting it as 933 Kelvin. So they have asked how much is the increased. Okay, so the increase is nothing but 933 minus 560, which is equal to, when you do this, you'll be getting, it is 373 Kelvin. So 373 Kelvin is the right answer. Okay. Okay, the 18th problem. See, in this problem, they given, in a cold storage, ice melts at the rate of 2 kg per hour. Okay, see the videos on. Okay, so in a cold storage, ice melts at the rate of 2 kg per hour. Okay, so here it is melt rate of 2 kg per hour. When the external temperature is, so when the external temperature is 20 degrees Celsius, okay, the atmospheric temperature is 20 degrees Celsius. Find the minimum power output of the motor used to drive the refrigerator, which just prevents ice from melting. So now we're going to use a refrigerator to maintain the temperature of the ice, so to prevent the melting of the ice. Okay, so what could be the power output of the motor to drive the refrigerator in which it could maintain the temperature of the ice? That is the question asked. Okay, so mass of the rate in which ice melts is given as 2 kg per hour. So the latent heat of ice is given in calories per gram. So we have to convert the mass into, so 2 into 1000 by 3600 in terms of seconds. So it will be, we do the calculations, it will be 250 and 900. So it will be equal to 5 by 9 calories per second. Okay, so the mass. So now what could be the heat to be observed for the refrigerator to maintain the temperature constant is, the heat observed will be equal to mass into latent heat. Mass into latent heat. So here what is the mass here? Here we have 5 by 9 into the latent heat is given as 80. So which is equal to 400 by 9 calories per second. Okay, so when you do this calculation, you will be getting it as 44.4 calories per second. But we want the heat in terms of joules. So I am going to multiply this value into 4.184 because 1 calorie is equal to 4.184 joules. Okay, so when you multiply this, you will be getting approximately 185.9 joules. So will be equal to 186 joules. So we have found the value of Q. So in case of refrigerator, you know that COP is equal to the heat to be observed. That is, this is Q2 by work done. But we have not found the value of COP. So COP value is in terms of temperatures. See, the external temperature is 20. The high temperature is 20 and low temperature is temperature of the ice, that is 0 degrees Celsius. So it will be the that is here T2 is equal to 0 degrees Celsius and T1 is equal to 20 degrees Celsius. So when you convert into Kelvin, 0 is 273 and 20 means it is 293. Okay, so here 273 divided by 293 minus 273, it is equal to 273 by 20. So COP we have got as 273 by 20. So when you equate it with Q and the work done, so when you equate with this equation, so COP is equal to Q2 by W. So 273 by 20 will be equal to this value. We got it as 186 by W. Okay, so from this W will be equal to 186 into 20 divided by 273. So when you do this calculation, so here it is joules per second. Okay, so when you do this calculation, you'll be getting the work done in terms of 13.6 watt. So if the W is given in watt, it means it is the power required. This is the power supplied, 13.6 watt is the power output required to run the motor to satisfy the conditions. Okay. So option D will be the right answer. So we have solved 18 problems in this video, and also we have displayed a Google form in the description box. So kindly you make use of it for your practice. Okay. Thank you.